Okay, so this is a continuation of the previous lecture. So, as we have discussed earlier, the rocket propulsion can be achieved by burning high energetic material within the combustion chamber. So, during that moment, the amount of mass that consumed, the amount of propellant consumed by burning it through and ejecting it through the rear part of the rocket. So now let's see what are the rocket propulsion systems. The rocket propulsion systems may be classified in many ways. One of the way we classify rocket propulsion as according to the energy source. So based on energy source, we classify the rocket propulsion as chemical propulsion, nuclear propulsion, or solar propulsion. So in chemical rocket propulsion, as we have discussed in last time, we have three types of propulsion: solid propulsion, liquid propulsion, and hybrid propulsion. Okay. And when we come to nuclear, there is a nuclear fusion or nuclear fission. So that are the type of እየሰማችሁኝ አይደለም አይደለም? Hello?
ይሰማል።
We cannot
ይሰማል፣
hear your
ይሰማል።
voice. የሚል ዘውዱ ጋር ዘውዱ ይሰማል?
ዘውዱ
Hello ዘውዱ ዘውዱ Hello hello
ምናልባት የኔትወርክ ችግር ይሆናል።
maybe still
የኔትወርክ ችግር ምንድን ድምፅ በጣም ብዙ ጊዜ ይጠፋል።
okay
ሄሎ ዶክተር የኔትወርክ ድምፅ እየጠፋ ነው ዶክተር።
የኔ ችግር ነው ኔትወርክ እንግዲህ አክቲቭ ነው። ኦኬ እስቲ እንደምንም ቶለሬት እናድርገውና እንትን በሉ። Okay, so another classification is by their basic function. Some of the rockets are used as a booster stage. That means in most rocket propulsion, we use booster rockets for the initial startup of or to bring the rocket to an appropriate altitude. We use some boosters. So that boosters will send the rocket to somewhere and then they will remain. And others are sustainers. And we can classify it again attitude control, orbit station keeping rockets, and so on. Again, by the type of vehicle, they propelled. Sometimes we propel it from aircraft, or maybe from missiles, or some assisted takeoff may be used. So based on that, we classify rockets as aircraft, missile, or assisted takeoff type, or space vehicle. Okay. Another method of classification is by their size, by their type of propellant. So by their size, small rockets or big or something like that. And by the type of propellant, for example, maybe the propellant can be solid propellant or liquid propellant or hybrid propellant. And the type of construction, that means geometric construction of the rocket. Again, by the number of rocket propulsion units used in the given vehicle. And finally, by the method of producing thrust. So these are the way how we can classify propulsion type. So this is a simple construction of some rockets. Okay, we have some staging rockets at the tip, primary electrical system components. There are also igniters which can help us to start up the ignition of the whole system. We have EPDM internal insulations. Okay, field joint with redundant seals. Okay, again, 88% of solids HTPB. Okay, HTPB propellants means this means hydroxyl terminated polybutadiene type. HTPB means hydroxyl terminated polybutadiene. So these propellants may be used. There are some central segments of rockets, steel attachment rings. Okay, so these overall components. Okay, yeah. So this is a rocket construction. How the rocket works? Yeah, we already discussed in last time. Okay, so according to our discussion, the working principle means the thermodynamic expansion of gas in the supersonic nozzle is here. The word supersonic nozzle is the nozzle designed for supersonic application. Okay, is utilized in most common rocket propulsion. And the internal energy of the propellant is converted into exhaust kinetic energy. Look, there is an internal energy in the combustion chamber, which converted into exhaust kinetic energy, and the thrust is also produced by the pressure on the surface exposed to exhaust gas. Okay, so we can see that in the next slide. Similarly, thermodynamic theory and generic equipment, which are used for jet propulsion, rocket propulsion, nuclear propulsion, laser thermal propulsion, or solar thermal propulsions are and electrical. So these are some of similar applications that we can obtain from rocket principle. Look, this is the principle. Look, you have pressure of the combustion chamber, which is perpendicular to the surface area of the given pressure vessel. So our combustion chamber is a pressure vessel, okay, on which a stored matter or the propellants are highly stored there. So temperature in the combustion chamber is here. Again, area at throat. Throat is the minimal dimension of the nozzle. So the minimum dimension on which high pressure, low velocity gas are come out from this point, and then it will start to accelerate in high rate when it comes out here. So this is the exit area, exit pressure, exit velocity. So the conditions we consider is, for example, we can call this as 1, 1, 2, 2, and 3, 3, or C condition, T condition, and E condition. Why? Exit, throat, and combustion chamber. So based on that, we can design our vehicle. Okay. So in the combustion chamber, there is chemical energy. And when it comes to around here, it is thermal energy, because there is high heat produced inside the combustion chamber, and the thermal condition will, or the thermal energy will try to accelerate through the throat. And then once it passes the throat, it starts to accelerate, so that it is kinetic energy. It produces kinetic energy or the momentum. Okay, so that can be, and the amount of vehicle velocity change from time to time, which is equals to delta U, which is equal to exit velocity times ln of m naught over mf. This is called the rocket equation, or Tsiolkovsky rocket equation. We call this is the Russian scientist in 1903, Konstantin E. Tsiolkovsky. He developed this kind of equation. Another is the amount of thrust that we can get from our this rocket design is the momentum, change in momentum plus pressure exit minus pressure atmospheric times area exit. So this is the previous equation. So this gives you m dot times VE, because the one which change from time to time is the mass. Okay, here mass is the changing quantity. Okay, so that dMe/dt, that means m dot, that is the mass flow rate, times exit velocity. So this term is called the momentum thrust, and this is the pressure thrust as we have discussed earlier. Okay, this is a kind of classification of rocket propulsion. So chemical propulsion is this: electrical, iron, thermal, nuclear. Again, when we come to chemical propulsion, solid, liquid, and hybrid. And if liquid is there, monopropellant, bypropellant. This is the composition of the propellant. Okay, sometimes we use monopropellants, sometimes we use bypropellants. So bypropellant having constituents more than one. Okay, so when we are summarizing, we know the three laws of Newton's three laws. One of the law is the law of inertia. And the second one is the law of motion. And so the third law is the law of action and reaction. So all these three laws are applicable in the rocket propulsion. Okay, so the second law is the law of momentum, that is the law of motion. So that allows an object to move forward because of the change in momentum. Okay, so the action and reaction law are also applied. Okay, so all of three laws are there. Okay, we have four types of propulsion systems. Four types. One is cold gas system, another monopropellant system, and the third one is bypropellant system, and the fourth solid motor system. So this solid motor system uses solid propellant, that solid oxidizer, solid fuel. Both the fuel and oxidizer are solid in this case. But these are monopropellants, and bypropellants are liquid propellants. And another one is the cold gas system, or the propellant which used in cold storable system. So the selection of our propulsion system type has some substantial effect on the total spacecraft, and is a key selections. Okay, so this is kind of cold gas system. So it is called cold gas propulsion system. Okay, and another name is cold gas thruster. We call this. Look, there is thrusters are there. This is the ignition or the engine system. Okay, we use a gas. The propellant is considered as a gas. Okay, so cold gas thruster design consists only of fuel tank. So this is a fuel tank. Regulating valves, some regulating valves are also required. Again, propelling nozzle is required. Look, so the constituents are the tank, some thrusters or the regulating valves, and then the nozzle. Okay, they are the cheapest and the simplest form of constructions, and are most reliable propulsion systems. Okay, so these thrusters are used to provide stabilizing for the smaller space missions. Okay, so cold systems can provide multiple restarting and pulsating. So it allows us to restart and pulsate it. Okay, so these are one type. So the design of cold gas propulsion. Look, there are propellant storage here. Compressed liquid or gaseous propellant will be stored in this region, and then it changed to some gaseous form here, as you see. Okay, and then it tries to accelerate through this narrow section that is called throat, and when it comes out, the expansion of decomposed propellant will take place. So this area is for decomposing the propellant, and this decomposed propellant accelerates through the nozzle, and which expands. Okay, So that is the way how cold gas propulsion system works. Advantage and disadvantage of cold gas system. The advantage is a lack of combustion in the nozzle of the cold thruster allows it use in the situations where regular liquid rocket engines would be too hot. So instead of liquid, this one is actually the main advantage is it is very simple construction and the cheapest kind of. And since 16s, people use this type. But the disadvantage is cold gas system cannot produce high thrust. So the amount of thrust that we can gain from cold gas system is small. So another is cold gas thrusters are less mass efficient than traditional rocket engines. And the maximum thrust of cold gas thruster is, it depends upon the pressure in the storage tank. So it depends on pressure condition. And as the fuel is used up, the pressure decrease and maximum thrust also decrease. So this is the disadvantage of this type of propellant. So which kind of propellant we use for cold gas system? That is another. So propellants used in cold gas system can solid, liquid, or gaseous propellants. But the propellant needs to exit the nozzle in gaseous form. The intention is whenever the propellant comes out through the nozzle, it is in the gaseous form. We need it for in the gaseous form. Storing liquid propellant may poses some attitude control issues due to slashing of the fuel in its tank. So this is another issue related with this type of propellant. So when deciding which propellant to use, a high specific impulse and a high specific impulse per unit volume of propellant must be considered. So this is a design issue. This point is high specific impulse is one of the criteria for our selection of any kind of propellant, similar to for all propellant types. Another is monopropellant type. So this monopropellant use hydrazine composition, that is N2H4. This is the chemical form of the bonding of the hydrazine. So this monopropellant is kind of chemical propulsion system. It use chemicals like ethylene oxide, hydrogen peroxide, nitromethane, which are common type of monopropellants. So the constructional feature of monopropellants, it contains a fuel tank. This is a fuel tank which is filled with hydrazine, or it can be hydrogen peroxide, or it can be any nitromethane. So then it's used some thrusters. These are thrusters on it, and some bulbs are there. Then catalysts are required, and the nozzle. So this is a simple constructional feature of monopropellant. So the specific impulse is about 225 seconds. That is one of it is good behavior, and the thrust from 0.1 pound to several hundreds of pounds are available in this form. And the system is commonly chosen for attitude control and the mid-range impulse requirement. And the most common propellant in this case is the hydrazine. Okay, so hydrazine is N2H4. Okay. Another is bypropellant system. So this bypropellant system is kind of complex system when we compare them as monopropellant and cold gas system. Look, we have oxygen tank is required. Again, fuel tank is there. As the same, pumping systems are required. Pumps are required here. Again, turbines are required. Gas generators are there. Look, valves are there. So this is very complex system. Okay, it is very complex system than others. So this is pump feed rocket system for Bypropellant. Another is pressure feed system. Look, this is the pressure feed system. There is high pressure gas are there. Oxygen tank and the fuel tanks are there. There are valves, and then it is connected to this system or the rocket nozzle, and then the nozzle will start to mix both of this fuel and the oxidizer together inside here and make burning. So once it burns, the high pressure gas comes out through the throat and then accelerates. So that is the method. So these Bypropellant systems are two types: pump feed system and the pressure feed system of rocket. So this is a Bypropellant system. The fourth one is solid motor system. So አንድ ሰው ወጥቷል ከእናንተ መሰለኝ።
ማንን እንጃ ማን ነው?
I don't know.
ኦኬ ጌች ነው መሰለኝ።
Okay, so another, the solid motor system, it consists solid propellant. There is a solid propellant here. Okay, it consists igniters, igniting system. The red colored indicates igniter. It consists the convergent divergent nozzle, and it consists some casing, the motor case, the casing or the shell, and other systems. Okay, so this is solid propellant system. So when all the impulses to be delivered in a single burn, and the impulse can be accurately calculated in advance, solid motor systems are a candidate one for such a system. Okay, so it is applicable for planetary orbit insertion and geosynchronous APEG burns. We use solid propellant system for such applications, and the specific impulse is about 290 seconds. Okay, so if the single burn criteria is met, solid propellant system provides simplicity, reasonable performance, and less cost compared to the monopropellant system. But the worst scenario of solid propellant system is once you ignite it, you cannot terminate. It will fully burn. So that is the worst situation. So let's see the comparison between these types: cold gas, solid motor, monopropellant, bypropellant. So cold gas use nitrogen gas, ammonia gas, furan, helium. These are the cold gas which can be stored in hypergelic or kind of. So they can provide high pressure and the volume of ISP, when a specific impulse is 50 to 75 in this case. The thrust range is from 0.05 to 200, and the average bulk density is given here, 0.28. Actually, this A represents some constant actually. And when we come to solid motor or solid propellant, it uses organic polymers, which are the cast form of polymers. It uses also ammonium perchlorates. It uses also powdered aluminum as a fuel. Okay, ammonium perchlorate, organic polymers. This combination gives us some chemical combinations, and the ISP is from 280 to 300. and the thrust range is 5 to 50 times 10 to the power of 6 Newton. That is a big thrust. Another monopropellant can be hydrazine or hydrogen hydrogen peroxide. This is hydrogen peroxide. This is actually ammonia. No, this is hydrazine, hydrogen peroxide. So these are used kind of exothermic decomposition in the energy source, and produces 150 to 225 second of ISCP. Another is bypropellant. So it uses oxygen and RP1. This RP1 is one of the composition. Again, it can use O2 and H2. Okay, so this is liquid oxygen, liquid hydrogen. So liquid oxygen is called LOX, LOX, and the H2 is a liquid hydrogen, which gives you 450 ISCP per second. Here, N2O2 and MMH, these are the compositions. N2H4, UDMH, F2 and N2H4. These are the combinations of the bypropellant. Okay, so this is the comparison between various propellant types. So when we come to chemical, So when we come to chemical propulsion system, it uses chemical reactions to release energy and accelerate gas to generate thrust. Okay, this system produces relatively large thrust in a relative short period of time. So what we need is to produce large amount of thrust within short period. So that can help us to accelerate our object in very fast manner. So chemical rocket engines use fuel to burn and oxidizer to react with fuel. Okay, so together they are referred to as the propellant. Okay, so as the propellant reacts inside combustion chamber, the chemical reaction produces hot gas, and the energy from the combustion reactions of the chemical propellant in a high pressure chamber goes into heating, reacting produce gas to the temperature of 250 to 2500 to 410 degrees centigrade. This is high amount of temperature, so on which some metallic substance can easily melt. Okay, so these gases are subsequently expand inside the supersonic nozzle, okay, and accelerates to high velocity. The velocity of acceleration of the gas are expected to 1800 to 4300 meter per second. That is high acceleration. Okay, so now the classification of chemical rockets, as we have discussed previously, solid propellant rockets, which use solid propellant, that is, grains are solid here. This is the propellant. There is an ignition charge here. Okay, this is the casing, the motor case. This is the outer case, is the motor case, and there are some sealing. This is the nozzle. Okay, there are also insulating substances, the material which separates the external casing from the internal hot surface. We need some HTPB kind, means hydroxyl terminated polybutadiene type of sealings are required. So this is the constructional feature of solid propellant rocket. And when we come to liquid propellant rocket, you can see fuel tank filled with fuel. Oxygen tank is filled with oxidizers. And there are separate pumps for each of them. This is the pump. And there are feeding systems to the combustion chamber. This is the combustion chamber. So all the fuel and oxidizer both together ignite inside of the combustion chamber and then accelerates through the throat. And the mass flow rate will take place in high speed at this region, that is diverging region. Here it is converging region, there is a diverging region. So through the exhaust, the high pressure gas will escape through it. Okay, so this is the exit region, this is throat region, and this is the fuel tank and other thing. So from that, we can find the thrust equation here. There is also hybrid propellant. This is hybrid propellant, you see. It contains oxidizer tank and solid fuel grain. The fuel is stored as a solid, which is grain, and the oxidizer is stored as liquid. So it is in liquid tanker. And there is an igniter which helps us, which facilitates the initial ignition of the system. Okay, and there is also a nozzle here. So this is a hybrid system. So these three are called chemical rocket system. So this is the solid propellant rocket. Look, the component part of solid rocket. Nozzle is one of the one of the part. Propellant grain is another. Igniter is another such component. There is metal structure or known as casing, and also insulation system. This is the one which separates the internal hot system from the external surface. So that is insulation system are required. Yeah, so this is a solid propellant rocket system. Yeah, this is also the same solid rocket. It seems like this. Okay. Yeah. So in solid rocket motor, we simply write it as SRM, that indicates solid rocket motor. The propellant consists of one or more piece mounted directly in the motor case, which serve both as a propellant tank and a combustion chamber. So the design of our combustion chamber or the solid rocket motor, it serves as a propellant tank as well as the combustion chamber. So every ignition system will take place inside of it. And the ignition may be from outward to inward or from inside to outward. If it is from inside to outward, then it is called progressive burning. If it is from outward to inside, then it is regressive burning. And there is also a neutral type of burning if both of them take place. So most propellant charges are formed by pouring viscous mix into the motor case with suitable mold fixtures. So there are mold fixtures. So we prepare the slurry of viscous mix of the propellant. Okay, we pour it into the mold cavity, and then we can cast it. It is method of casting. So the propellant solidifies. Now we usually call it polymerization. Okay, you are familiar with what the meaning of polymerization in your chemistry. And the mold fixtures are removed and leaving the propellant bonded into the motor case with suitable shaped perforation. So the perforations are some shapes. Sometimes we create a star shape of perforation. We can create some kind of webby or any kind of perforations will be created on that shape in our molds. So during operation, the solid burns on the exposed inner surface. Okay, the propellant burn from exposed inner surface. For example, we have this inner circular slot. Through that surface, the ignition will take place. This burns away at predictable rate to give a desired thrust. Okay, so That is the method of how we can. So one of the part is solid rocket motor case. Motor case is the external shell which encloses overall internal system. Okay, so the rocket motor case consists of a steel or aluminum tube with a head end dome. Head end is doomed to and contains some igniter in it. Look, if I go back, let me show you. Here there is dome-shaped things are there. There is igniter holders are here. This is the holder for igniter. Okay. So this type of construction. So rocket motor case have insulation on its interior surface. Why? For the protection against the thermal failure. If there is no insulating surface, the temperature will propagate outward and will cause the failure of the whole structure. So rocket motor cases are made from high strength steel. In most cases, we can use maraging steel. Maraging steel is the one. Or by filament winding of high strength fiber on the suitable form. If we are making composite casing, then filament winded kind of casing is required. So in motor case, the front and aft domes are wound as integral part of the case with suitable opening and fixtures. So this is just so this is the propellant, the solid propellant. How it is burned and how it is energy is released from it. This is the method. Okay, igniter is situated here. Once it ignites, immediately the inner surface is started caught by fire and high energy gas are coming out into the nozzle. So this is burning surface inside here. Or there are some surfaces which are inhibited, not allowed to burn, and another surface are exposed to burn. Okay, burned propellants are coming out like this. Okay, there is engine casing, metallic engine casing is here, and heat resistance material. Here there must be heat resistance material. Why? Because a kind of erosive kind of burning is take place here, so that in order to maintain or survive the casing or the nozzle from heat, we use heat resistance material like yeah, you know what are heat resistance material from your material point of view. Okay, so materials for solid propellant. So how we can prepare solid propellant? One of an important ingredient for solid propellant is ammonium perchlorate. Okay, that is granular oxidizer. This ammonium perchlorate is an oxidizer, and powdered aluminum is a fuel.